Yeah, hi all. Welcome to this IT classes once again. So today we are seeing, in the previous lecture we have seen BFS. So today we are going to see in this lecture BFS, breadth first search. So suppose instead of graph you are given with a tree. Okay, so once I will try to apply the breadth first search on a tree, which will give you more understanding. So what is the difference between tree and graph? Tree don't have any loops. Okay, or any node to the previous node. Okay, it's unidirectional kind of thing. And in graph we may have loops. So each tree is also a graph actually, but each graph is not a tree. Okay, so let's consider a tree with many nodes here like this. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then let's make it like this also. Okay, 12, 13, 14, 15, 16, 17, 18. So algorithm of BFS says that we start from any source node. So let's start from here, from the root node. Okay, now as per BFS algorithm, the traversing will happen like this. First, it will be level order. If we run BFS on a tree starting from the root node, it will be level order traversal. Okay, this will be first one. Okay, now it will print it like this. If we run the BFS here, one first, then it will print 2, 3, 4. Okay, second level. Okay, so this can be also called, if we run BFS from the root on the tree, it can also be called level order traversal. Level order traversal. Level order traversal. Okay. It means if somebody asks you that I want to run level order traversal on a tree, any tree, binary tree, non-binary tree, any kind of tree, okay, then we can run BFS here. I will write down the algorithm. First, let's see. If we run the BFS here, it will print 1 first, then 2, 3, 4, then 5, 6, this level, okay, this level, 7, 8, 9, 10, 11, 12, then this level, okay, 13, 14, 15, 16, 17, 18. This is how it's going to print. This is how it's going to be traversed. Okay. So BFS and BFS, breadth first search and depth first search are nothing but traversing algorithm. Going through all the nodes of the graph, starting from a node, or going through all the nodes of a tree, starting from the root node or any other node. Okay. So these are traversing algorithm, nothing else. Okay. So let's see how we get this level order traversal. What could be the reason? In DFS, I told you that even if we use recursion or a manual stack, like a explicit stack, not implicit. Implicit means using recursion, we are using stack. So that is called implicit stack. If we use the explicit stack in the code by using stack data structure, that is the same thing as calling the DFS. So in BFS, that first search, we are going to use queue. Okay, how it's going to happen? We will have a queue. For example, this is a queue. Okay, under this queue, what we will do, first we will put the source node. Okay, so let's assume here the source node is the root node. So we put first here, one here. Okay, then the first thing is put nodes. Currently starting, if we are starting from the source node, we'll put the source node, put nodes in the queue. Now calculate the size of the node, the second size of the queue. Size of the queue. The current size of the queue. Okay. And while popping or putting, we will iterate it as per the size of the current size of the queue. Okay. So the current size of the queue is but 1. So whenever we are putting the neighbors of this one node 1 in the queue, before it, we will pop for current size of the queue, okay, so current size of the queue is 1, as there is only one node in the queue. We will pop it and we will put all the neighbors 2, 3, 4. Okay. In the second iteration, we will again calculate the size of the queue, which is 3. So we will pop for 3. For the next 3 iteration, we will pop the nodes. For in queue, we know that queue we put the node at this endpoint, and we pop the node from this endpoint. Rear and front logic is there, right? In queue, we have rear and front logic. So basically, we put the node at the rear and we pull the node from the front, something like that, right? So at one endpoint, we are putting the node like this, and from another endpoint, we are popping the nodes. So size is 3. So we pop 3 times. Okay, if we pop 3 times, we pop 2, and we put its neighbors, which put its children, which are 5, 6, 7. Okay, then we pop 3, we put its neighbors, which are 8 and 9. You can see 3 have 8 and 9. Then we pop 4, and we put 10, 11, 12. Now see what happens. We stop here. Okay, we stop here. So this is our first level. This is our second level. This is our second level. Okay. So now whatever is present right now in the queue after popping the second level is the third level. So we can pop the third level. And after popping the current size, what is the current size? 1, 2, 3, 4, 5, 6, 7, 8. So current size, it means third level contains total how many nodes? 8 nodes. So you can pop these nodes and again push the children. Okay. So this is how you can print the level order traversal. This is how you can do level order traversal. So one of the benefit of BFS is we can do level order traversal in the tree. Okay. And why is it breadth first search? Because we are going in all the directions at same point. Okay, so first we have checked 1. Then we are going to search 2, 3, and 4. 2, 3, and 4. We are not going directly from 2 to 5 before checking 3 and 4. Okay. So what we can do here, if we run the BFS, how can we run the BFS? We put the root node. I'm talking about tree right now. Put the root node. If I want to do level order traversal using BFS, what I can do here. Okay, sorry. Level order traversal I want to do. So we put root here. Okay. And initially, what do we do in the BFS? We initialize a queue. Okay, we initialize a queue with name queue. In this queue, basically we push the root. So root will be pushed from this end, right? This end, and pop from this end. In stack, the pushing and popping will happen at the top only from one end. That is why whatever we pushed at the last will be popped first. In queue, whatever we have pushed first will be popped last. Okay, so it's first in, last out. Okay, first in, last out. Queue works like this, and stack works like last in, first out. Last in, first out. And we have seen the many application of stacks previously, right? Postfix expression evaluation, other things. So here in the queue, we push the root. And now, if you want to do level order traversal, what we do, we'll go like this. While queue is not empty, whatever function the language required, we check that queue is not empty. We will keep on running this. And now we go level by level. First, we calculate the size of the queue dot size. Okay. We calculate the current size of the queue, which is basically current level is present. Current level elements are present in the queue. So this is the size of current level. Okay, and we iterate for that size. We say that while S is greater than 0, S is greater than 0, we keep on doing this. Okay, so we pop, we do like a print q dot pop. So whatever we pop, we will print it. Okay, and whatever we pop here, we'll push those elements at the front of the queue. So we do like a push all neighbors. Okay, sorry, let me go to the next page here. So here the while loop will look like this. While queue is not empty. Okay, queue is not empty. It means something is present in the queue. Right now, only one node, root node is present. We are starting from the root node, so only root node is present in the queue. Okay, and we calculate the size as q dot size. So this is the current level size. Current level is first level right now. Only root node is there, and while size is greater than 0, size of current queue means this level is greater than 0. We will keep on appending or keep on pushing items in the queue, but we will iterate for current level size only. We will iterate for current level size. Okay, so we do like a element equal to, or you can say node equal to q dot pop, and we push all the neighbors of the queue here. Q dot push all the neighbors of this element. Okay, this element here. All the neighbors of this node will be pushed into the queue. Okay, and we do s equal to s minus 1. Yeah, that's it. So if you want to print it, print the current node, so you can print also after this statement, you can do print node. So this program, before it, what did you do? We do q dot push the root node before this loop. We started from the. So this program is level order traversal. Why it's level order traversal? Because here we are calculating current level size, and we are printing the current level. And parallelly, we are pushing the neighbors also. Like neighbor in tree, you can say apparently we are pushing the children of the current level also. It means the next level is also being pushed into the queue. But we will pop until what? Until the current level. If somebody asks you what is the level, you can here initialize level equal to 1. And here you, after each while loop, you can do level equal to level plus 1. And here you can print level. This is how you can do level order traversal. Anyway, if somebody asks you that what is the level of the current node which you are printing, then you can do this. If somebody don't ask you, you can simply run this loop. This will be level order traversal. So using BFS, we can do level order traversal. The idea behind the BFS is we will spread into the breadth. We spread into the breadth. If this is the graph we have, okay, 1, 2, 3, 4, 6, 7, 8. So if you are starting from this node, this is a possible BFS. What is the possible BFS? 1. Then the next level could be this one, 2 and 3. So we'll pick 2 and 3 in any order, 3 or 2. 1, 3 or 2 is also a answer. 1, 2 and 3 is also an answer. Okay. So if we have printed 2 first, it means 2's neighbor will be pushed into the queue first. Okay, so what else neighbor are there for 2? Only 4. So we have pushed 4. So once we pop 3, we can see all the neighbors, no neighbors will be pushed. So now once we pop 4, we will push all the neighbors, 6 and 5. 6 and 5. Once we pop 6, all the neighbors will be pushed, 7. Okay, once we pop 5, we will print 5. And what all neighbors of 5 are there? No neighbors. Once we pop 7, we can print 8. Okay, now if you see levels here, this is our first level. This is our second level. Okay, we are going in breadth, right? We are going in breadth. From 2, we didn't go to 4 before traversing 3. Okay, in depth, we will go from 1 to 2, 2 to 4, 4 to 6, then 5, then 7, then 8, or from 1 to 2, 4, 6, 7, 8. After that, we will do 5. So in depth first search, we go in depth first. The root, if this is the root in depth first search, if this route we can take it. Okay, all possible route from depth side we can take. In depth first search, we'll first traverse all the neighbors. Okay, so 4 have 2 neighbors, 6 and 7. And now see, this will be our third level. This is our fourth level. This is our fifth level. This is our sixth level. This is how it will print into the BFS. So if you consider any tree, once again, I'm repeating this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will print 1 first, then 2, 3, 4, where 2, 3, 4, then this 5, 6, this level again later, 5, 6, 7, 8, 9, 10. This is how it's being printed by using Q. Okay, so let's see the application of BFS and DFS. So DFS have, you can go and check the program also of this DFS, because DFS can have many applications. These are the popular applications. First one is, like if we perform DFS on unweighted graph, it means node, the edges don't have weight. Okay, so this is a weighted graph. If node edge don't have weight, then it is unweighted graph. Okay, it is unweighted graph. So if we apply the DFS on unweighted graph, then it will create what? Minimum spanning tree. Okay, for all pair sorted path tree. Unweighted, here we can consider that each edge have equal weight. You can consider as 1. Okay, so something like this. So the minimum spanning tree I explained there in the algorithm, you can check. Each edge has same weight actually. So here we can create a minimum spanning tree by using DFS. If we apply DFS on unweighted graph, okay. The second application could be, we can detect cycles in a graph, okay, using DFS. Okay, so basically we have a algorithm in DFS. DFS is nothing but DFS can be used nothing but this this backtracking. So using that, basically we can see if the already visited node we are visiting again, we see that in DFS we have this visited array. Okay, that is also required for BFS also. Because I ran it on a tree only. We know there is a parent-child relation, but in graph there is no parent-child relation. So in BFS also we require visited array. Okay, so using that we can identify backtracking. Using the backtracking algorithm, we can identify basically no backtracking. DFS is backtracking. Using DFS, basically we can identify if visited array contains some visited nodes, and if we are visiting that again, we are not going from that node again. But if we are going to that node again, it means there is a loop, there is a cycle in the graph. So we can identify that. The third point is we can perform topological sorting. So topological sorting, I think I explained in database. Topological sorting I've explained in database. That is performed using DFS algorithm only. So we can perform topological sorting also. Okay. So this can be done using DFS. So this is basically used for what we had topological sorting we used for certain properties, certain things like right, and in DFS also, and in networking also. In networking also we required the topological sorting. So there we can use. Mostly there is a topic there in database where I have explained the topological sorting. You can go and check that. And then we have the fourth point. Using DFS, we can identify all strongly connected components of the graph. So if our graph is like this, okay, this is a whole graph. This whole is a graph, right? We have component 1, component 2, component 3. Using DFS, we can identify all strongly connected components, right? So we can count, we have 3 components. There is one more algorithm which is used for identifying strongly connected component. There is one more data structure which is called union find. This is not part of your course, but you can go and check union find algo, which is very interesting algorithm, very simple algorithm. Using union find algorithm, we can identify all the connected components, not only one strongly, all the connected components. So using DFS also, we can find out all the connected components. Okay. So strongly connected, what is the definition of strongly connected component first? So I just realized you may not know the strongly connected component means. It means if there is a path between each and every vertex, each and every pair of vertex, then that is called strongly connected component. For example, this is also a strongly connected component, right? From V1 to V3, we have a path. Okay, like this, we can go. From V1 to V3 also, from V3 to V1 and V1 to V3, we have a path. So if we have a path from V1 to V3 and V3 to V1, then that is called strongly connected component. This I have written undirected graph, but we could have a directed graph also, right? In that case, the strongly connected component we can identify. And for that, we can use union find algorithm also. Very easy algorithm, very simple and plain algorithm. If I got the time, I will explain this algorithm, but it's not part of your course. Okay. Now, those are the application of DFS. What are the applications of BFS? Let's see. So breadth first can also be used for certain situations. One is BFS is used in Ford-Fulkerson algorithm. Okay, so that I explained in algorithm part, the Ford-Fulkerson algorithm. The Ford-Fulkerson algorithm actually runs using BFS only. Okay, So now third thing is pathfinding algorithm. Pathfinding algorithm is based on BFS or DFS. Both can be used. Okay, so in a given very dense graph is there, like very huge, very big graph is there, something like this. Okay, very densely populated graph. Okay, we have too many nodes. Then what happens? We have to find out the path like this from this node for V1 to V5, for example. Then these algorithm we can use BFS or DFS. DFS also can be used. Generally, we use BFS only. Because if we have so many nodes, DFS can fall into a very deep level of, you can say, connection. So what may happen that here, the DFS, if DFS start from V1, the DFS can go like this from here to here to, like it can skip, it can go in very deep path, this path, and it have to go back and backtrack from this again. So that's why we can use BFS. I think BFS is better in that case. Also, in networking, we want to broadcast some packet. We use BFS algorithm, not the DFS algorithm. So broadcasting, which is part of your computer network course, CN, that uses basically BFS, that first search. Okay, and GPS system also use heavily BFS. Okay, so these are some applications of DFS and BFS. So in DFS, generally in examination, people ask that DFS uses what. So if somebody asks you that, okay, DFS can be solved using stack, okay, that's okay. But can I use it using recursion? Recursion, you can say yes. But internally, recursion also uses stack. If we are using only recursion, not explicit stack, that is called implicit stack. Implicit stack, okay, system stack. Anyway, we are using stack. And BFS, okay, sorry, BFS uses what? Queue. Okay, queue. That is why we do level order traversal. So here we have depth, here we have breadth. Okay, so the difference here is the DFS will go like this. It will cover one part first. It will try to cover this one first. Okay, and BFS will go like this. It will cover this one first, then this one. So it is expanding in depth. The BFS is expanding in depth. Okay, so in breadth. The BFS is expanding in breadth, and DFS goes in depth. Yeah, so that's it from my side. I see what all topics are missing. I think I covered most of the topics of data structures, different kind of data structure which all you required for interviews, any examinations, any government examination, PSU or GATE examination or any other examination you use. So I have covered all those basic fundamental data structures and previously explained algorithms also. So you can connect these two because to use algorithms, you need the data structures. Okay. So to first you can go through the algorithm subject. There I explained what all things are required, like mean, heap, max, heap we have covered here. Okay. So Hoffman encoding we have seen, right? Hoffman encoding of Hoffman encoding. I'm just giving an example. Hoffman encoding, file merging. So these are what? Greedy techniques. Greedy algos. Okay, so greedy algos. And if you go back and check here, each time we require minimum. In Hoffman, we require minimum. Here we require minimum 2, top 2. Minimum 2, or here also I think minimum 2 we require. Minimum top 2. So what all data structure can we use? Whenever we require something minimum, and you again wants to calculate, recalculate the minimum. Okay, so basically we can use here mean heap. Okay, so mean heap is almost complete binary tree. So it is a almost complete binary tree. Almost complete binary tree. It can look like this, okay? So here we have minimum element. We can delete this. Once we delete the minimum, we can basically pop this minimum. The next minimum, either this one or this one, will come to the root, and we can get the next minimum also. We can sum it up again, push it into the tree, and we'll get the minimum at the top. So this is how min heap can be used. Min heap, HEAP. Okay, min heap can be used for Hoffman encoding, file merging technique, job scheduling. In job scheduling also we require the minimum or maximum. Max heap can be used there. So you can be innovative there. Once you know the data structure, you know the algorithm, you can combine these two and solve many problems. This is how the programming works. In programming course, we will see the variable initialization, the static variables, and some for loops, and some loops are there, right? Some looping structure, some recursive methods are there. So that is kind of aptitude they wants to ask. Programming aptitude they will ask, right? But this is the real programming actually. If you want to solve any problem, any networking problem, any real life problem, any database problem, we use these algorithms and data structure together. And all the data structure which I've explained, all the data structure are in the world basically you can say variations of the data structure which I have explained. They are just variations. Okay, like we can use multiple arrays to implement a stack. We can use a single array to implement a stack, and we can use a array to implement min heap also. So this is how basically we can proceed and solve our problems. So thank you all for this course. I think I'm done with this course. Whatever is remaining, I may try to take one or two lectures more. But I think for now, that's it. You can go to the course and check it. If you are missing any topic, you can contact me using iitiansgateclasses. Thank you.